Good morning to the judges of the 2020 WEF Tech Connect Student Design Competition. In this presentation, my team and I will walk you through step-by-step of our disinfection treatment design, which we created to upgrade the St. Joseph's wastewater treatment plant in South Bend, Indiana. But before we go into the design details or why we chose this project, I would like to introduce all of us who you will hear from today. My name is Juliet Bertram, and I'm a junior year environmental engineering major and sustainability minor at the University of Notre Dame.
I'm Patrick West. I'm a senior at ND studying environmental engineering with minors in energy studies and theology.
My name is Kiara Smarata, and I'm a senior chemistry major at St. Mary's College and a junior environmental engineer at Notre Dame.
My name is Michael Dunn, a junior studying environmental engineering at the University of Notre Dame.
As a general overview, today we will address combined sewer overflows in the St. Joseph region, along with South Bend's long-term control plan to contextualize the need for an improved wastewater treatment design. Then we will share our project goals and introduce the South Bend wastewater treatment plant. Our goals include chemical alternatives to keep the existing disinfection tank. Goal 1 proposes implementation of sodium hypochlorite, Goal 2 proposes utilization of peracetic acid, and Goal 3 proposes adding a new disinfection tank with UV hardware to upgrade flow capacity. After our goals, we will summarize our findings and compare our alternatives. Lastly, we will acknowledge those who have mentored and guided us along the way.
The city of South Bend, like many older cities located within the northeastern states, installed a combined sewer system designed to carry both sanitary and stormwater flows. Unfortunately, these combined sewer systems tend to be overloaded during extreme rainfall events, at which point they release a combined sewer overflow, or CSO discharge. These CSOs subsequently dump untreated sewage into rivers and streams in the surrounding areas. In South Bend's case, their nearby St. Joseph River has 49 of these CSO outfalls. Concerns about these CSO outfalls escalated over the years as their size and harmful impacts increased. Within recent decades, therefore, regulatory demands were finally adopted, which required cities to adopt corrective CSO remediation measures. In response to South Bend's particular CSO situation, the United States EPA issued a consent decree in 2011, which established specific steps to be taken for negating their CSO problems. With an estimated cost of roughly $500 million, the financial burden of this consent decree on South Bend was particularly painful since the city was already in economic decline and financially stressed. Furthermore, the city felt that there were many points in the consent decree which were redundant, unnecessary, and ultimately wasteful. A principal concept laid out by this consent decree was that the city of South Bend is required to design and implement a long-term control plan. This long-term control plan has 3 key requirements. First, the city must install new CSO structures for short-term storage of extreme stormwater flows. Second, the city agreed to develop and install a new smart sewer strategy where peak CSO flows can be temporarily stored within the city's existing sewer network. And third, the city is required to increase the wet weather flow capacity of its wastewater treatment plant to meet a 100 MGD peak flow. This particular upgrade will provide a significant benefit with minimizing CSO flows and impacts. The city's latter goal for upgrading their wastewater treatment options were then expanded to include 4 main outcomes. 1, to support full compliance with their consent decree. 2, to ensure necessary disinfection of the city's wastewater discharge under both average and peak flow conditions. 3, to upgrade their wastewater plant's flow capacity to a peak flow of 100 MGD. And 4, to upgrade the city's existing disinfection system in a fashion which would minimize and eliminate their current use of dangerous chemicals, specifically chlorine gas plus sulfur dioxide gas.
Here's a quick plant tour. First is preliminary treatment with bar screens and grit tanks. Next is primary treatment with 8 primary clarifiers. Then secondary treatment with 4 aeration tanks. Next, secondary settling with 7 settlers. Then disinfection with 2 chlorine chamber tanks, dechlorination with sodium bisulfide, and discharge into the St. Joe River. The existing disinfection system can handle 77 MGD peak flow with 2 parallel serpentine tanks with a minimum 15-minute contact time. To the right of the outlet contains separate storage rooms for chlorine and sulfur dioxide gas.
When building our design, my team and I focused on 3 main goals. First, we need to eliminate the presence of chlorine gas at the plant. The current serpentine tank disinfects water through the injection of chlorine sourced from Cl2 gas, which is stored on site and possesses a serious catastrophic risk to workers in the surrounding communities should these tanks be damaged or exposed. Additionally, the post-disinfection quenching agent sulfur dioxide is also in gaseous form, so we would like to change that to a solid or liquid form as well. This could be done in one of two ways. Either we continue the traditional route of using a chlorine-based disinfection system but with a solid or liquid form of chlorine and quenching agent, or we transition to a completely modern alternative chemical-based disinfection. However, with either of these above scenarios, we must still build a new disinfection tank to treat an additional 25 million gallons a day, as the contact time in the existing serpentine tank does not reach 15 minutes at the peak flow of 100 million gallons per day per Indiana state requirements. Looking closer now at our first goal, the use of liquid sodium hypochlorite is quite common in the US and around the world as a tried and true disinfection agent. It is safer to store and has a simpler delivery route than chlorine gas, though for the St. Joseph's plant that will mean they will have to remove the old hardware and install a new system for both the disinfection and dechlorination systems. For the latter part, we propose using liquid sodium metabisulfite. The dosing of the sodium hypochlorite and sodium metabisulfite will vary based on flows, but for chlorine will range between 5 and 8 milligrams per liter. The new storage tanks for sodium hypochlorite and sodium metabisulfite would have to be made of polyethylene due to their corrosivity. The storage space required for sodium hypochlorite compared to chlorine gas is slightly higher, though the overall storage capacity of each chemical will still sit around 25,000 gallons, and we plan to keep these tanks in a separate containment area in case of spills. In addition to the new tanks, the pipes will also have to be made of PVC to prevent corrosion and have new pumps purchased to deliver the liquid chemicals. We also must determine how to transfer the chlorine to the head of the disinfection tank from the current chemical storage location. Though it is widely used, sodium hypochlorite has a few notable drawbacks. First, its basicity can cause ions to precipitate as scale and accumulate on surfaces during the dilution process. To resolve this, the plant can either deliver the chemical to the tank undiluted or soften the water used to dilute the chemical. Second, the addition of sodium hypochlorite will raise the pH of the water, which St. Joseph's plant will have to monitor to ensure that the effluent pH is within the regulation levels. Third, the chemical has a very short shelf life, often losing over 20% per month, so this would require the plant to have frequent chemical deliveries. Finally, the disinfection byproducts as a result of chlorine reacting with organic matter are similar when sodium hypochlorite is used to the existing ones created from chlorine gas disinfection.
Our second goal involves an up-and-coming chemical alternative, peracetic acid, with the existing disinfection tank. Peracetic acid is a peroxide of acetic acid that serves as a strong oxidizing agent. Typical peracetic acid concentrations for commercial use range from 10 to 15% in the form of equilibrium solution between acetic acid, hydrogen peroxide, peracetic acid, and water. Currently, the EPA has approved of certain peracetic acid formulas for wastewater disinfection. For our treatment design, peracetic acid is advantageous for a number of reasons. First and foremost, peracetic acid eliminates the risks associated with chlorine gas. And as a strong oxidizing agent, peracetic acid exhibits widespread biocidal performance against bacteria, fungi, spores, and viruses. As the chemical breaks down relatively fast in wastewater, it has no residual toxicity and does not require dechlorination. Peracetic acid does not produce harmful disinfection byproducts, which are identified as a major drawback of chlorine-based disinfectants. Since peracetic acid is also a more powerful disinfectant than sodium hypochlorite, the dosing levels are relatively low. We're looking at 1 to 2 ppm. And unlike sodium hypochlorite, peracetic acid is relatively unaffected by variations in ammonia and organic matter. Lastly, efficacy up to pH 9 and long shelf life make peracetic acid particularly appealing for wastewater treatment. Peroxichem is a major peracetic acid vendor in the US. Their product Vigor Ox WWT2, designed for wastewater treatment, is a mixture of 15% peracetic acid and 23% hydrogen peroxide. The South Bend plant would likely receive tote deliveries or bulk deliveries of 4,000 gallons per truck. The mixture was EPA approved in 2006 and is very stable with a long shelf life of 12 months that far exceeds sodium hypochlorite stability. Peracetic acid pricing would be approximately 80 cents per pound, and dosing ranges from 1.5 to 2 milligrams peracetic acid per liter, and this would use standard chemical delivery diaphragm pumps. Again, implementation entails new polyethylene chemical storage tanks. We're considering 2 different tanks, each with an estimated storage capacity of 6,000 gallons. Safe containment would also be used in case of spills. For chemical delivery, a new pumping system includes new delivery pumps and stainless steel piping. Lastly, high-rate transfer pumps will be installed for bulk chemical transfer. Peracetic acid application and case studies are more widespread in Europe. Europe's largest peracetic acid system in Milan, Italy, uses 6 million pounds per year. Within the US, the largest peracetic acid system is in Memphis, Tennessee, which uses 30 million pounds per year for a 100 mgd system. Recently, WEF has also started investigating full-scale, backup, and UV peracetic acid hybrid wastewater treatment plant systems. An example of field data from a case study in Hannibal, Missouri is shown on the right. This graph depicts peracetic acid dosage versus E. coli and fecal coliform concentrations over time. As with any solution, peracetic acid has some potential disadvantages. Peracetic acid is more expensive than sodium hypochlorite per pound. However, this difference is offset by the fact that peracetic acid requires lower dosing levels and does not require an additional quenching agent. A table with a cost assessment is included below. And as a newer disinfectant, peracetic acid has yet to be approved by the Indiana Department of Environmental Management. Aquatic toxicity levels are the primary reason that many states have not adopted peracetic acid, because these measurements and regulations vary by state. With a fast decomposition rate, determining peracetic acid toxicity is difficult because peracetic acid breaks down before reaching the lab for analysis. On the contrary, peracetic acid's low-level aquatic toxicity is valued by other industries. That being said, peracetic acid also has applications in food, beverage, medical, and pharmaceutical disinfection. As an example, the FDA has approved of peracetic acid for disinfection of 90% of the chickens in the US.
Goal number 3 is to add a new disinfection system to add total disinfection flow capacity to 100 mgd. The current secondary effluent flow routing disinfection pathway is shown via blue arrows. The peak capacity for each clarifier is shown as well. You can see that clarifiers 6 and 7 on the west side of the plant are the largest clarifiers and can handle 25 mgd flow each. The proposed UV disinfection tank at the upper left-hand corner will divert flow from these two clarifiers to treat a maximum 25 mgd flow. The tank would be located at this approximate location. The outlet for this tank will bypass the existing disinfection system and rejoin existing flow to maintain one outlet. This flow diversion will be done using a slide gate or a pinch valve. A magnetic flow meter will measure the side stream flow to ensure that no more than 25 mgd flow is diverted to the tank. Data from this new flow meter will be connected to the plant's existing SCADA system to automatically control the diversion mechanisms. Other construction measures include shoring the western slope for construction and dewatering for the tank's foundation.
South Bend's third disinfection upgrade goal involves the installation of an ultraviolet UV disinfection system. The primary benefits of UV disinfection are the exceptionally low contact time and extremely low reactor footprint. At the same time, UV treatment also eliminates the use of chemical-based disinfectants whose use may lead to potentially harmful disinfection byproducts. Overall, the use of UV disinfection provides multiple overlapping technical, environmental, microbiological, safety, and economic benefits. South Bend's projected new UV system would take advantage of a recently developed technology marketed by one of the leading UV technology distributors, Trojan UV. Their new Signa UV system has been developed with a new solar lamp system, whose mid-range pressure bulb design offers the following unique benefits. First, high-intensity irradiation rate, which reduces both the number of necessary bulbs and the installation footprint area. Second, reduced energy consumption per bulb, which reduces overall energy demand. Third, adjustable electrical dimming, which allows control systems to trim applied energy to match existing wastewater flows. And fourth, long bulb life due to lower operational temperatures. This Trojan UV schematic documents the corresponding benefits provided by the new solar lamp systems in comparison to conventional low-pressure lamps, which are low intensity, low energy, and low temperature, as well as medium-pressure lamps, which are high intensity, high energy, and high temperature. In essence, their mid-range solar lamp option offers the best of both energy efficient and low bulb count benefits. South Bend's proposed Trojan Signa system would involve 3 parallel banks of lamp modules, each with a rated peak flow capacity of approximately 8.3 mgd. Each of these UV module banks would hold 18 individual lamps, for a total of just 54 lamps. This remarkably low lamp count will also help to improve operational maintenance challenges. With an anticipated overall footprint of 18 by 30 feet, this entire UV system will have a significantly lower space demand as compared to any chemical-based disinfection system, ultimately offering significant location and capital construction benefits.
So as we've mentioned, each disinfection method has its operational drawbacks and advantages, but we also wanted to acknowledge the potential expense associated with the construction and upkeep of each of these options, as price and budgeting are often a major deciding factor in deciding how designs are chosen. First, comparing the costs associated with upgrading the existing disinfection system, we estimate that converting to a peracetic acid versus a sodium hypochlorite system would be about half the cost, both in upfront installation and daily operational costs. This is in large part due to the lower concentration of peracetic acid needed to disinfect the water, about 2 ppm of peracetic acid versus 6 to 8 ppm of sodium hypochlorite, which would therefore require smaller chemical pumps and piping and also a less frequent delivery of the chemical. All in all, the sodium hypochlorite system would cost about $600,000 to install and $840 per day to operate. The peracetic acid system would cost about $300,000 to install and about $400 per day to operate. Though the savings from peracetic acid are significant, the value of the system is contingent on the approval of this chemical for use in Indiana state wastewater treatment plants, which has yet to occur. In addition to upgrading the existing tank, the St. Joseph's treatment plant must also budget for the installation of the proposed UV disinfection tanks. We estimate the installation costs for the UV system to be about $800,000, including labor, which makes its construction a large initial expenditure. This cumulative cost includes the Trojan system capital costs, which is about $450,000, the cost for constructing the 3-channel concrete tank, which is about $150,000, and the cost for constructing the hydraulic channeling between components of this new system for about $200,000. These UV system cost estimates are based on the advice given to our team by the Trojan Technologies design team in August 2020. This large sum is countered by its low daily operational costs, which would hover around $43 per day for average flows and around $130 per day during peak flow. The precise operational cost is highly dependent on the cost of electricity and provides a very energy-conscious option for the plant. We were very fortunate to receive wonderful advice and guidance from several individuals and groups, including the 2020 Notre Dame Civil and Environmental Engineering Senior Design Team, Jordan McCormick from American Structure Point, Inc., Professor Ernest Blatchley from Purdue University, Philip Block from PeroxyChem, which is now merged with Envonic, the design team staff from Trojan Technologies, including Adrian Peck, Jacob Klosinski from South Bend, Indiana's wastewater treatment plant, Craig Williams from Angola, Indiana's wastewater treatment plant, and Amy Smitley, the vice president at Arcadis.